Okay, let us start by covering the general philosophy of tuning with neural networks. I know that machine learning is not a super familiar ground to everyone. So, in this section, I am going to very gently cover the basic philosophy behind using machine learning and maybe show one or two figures of how neural network works. And then I will try to explain how to embed this into general workflow of controlling a quantum device. So in our lecture note from a machine learning school from which this figure is taken, we were trying to summarize what's the difference between this sort of new machine learning or AI-driven approaches to programming and traditional programming. So in a very bigger picture view, we came up with these two green and blue figures that sort of explain a different philosophy. In a traditional programming, you think about, given your input, what results you want to have, and then you build up the program just using your programming skills in Python. Let's say you write your for loops, you write your if statements, and you have a fixed thing that executes given your input mapping on the results that you want to calculate. In machine learning, the approach is different. We know in a lot of problems in practice, the program, the steps that you need to execute to get a desired result is not completely clear. So in machine learning, we want to learn from the data. So on the input side, we put an input, and as a desired result, we introduce a lot of data, and then the computation outputs something that will serve as a program that will map your input on a desired result. The way to think about is about this is something that is like standard machine learning example, that you have these algorithms that recognize dogs from cats. And think about how difficult it would be to write a deterministic program to really judge any figure of any dog or cat and really determine if it's a dog or a cat. That would be a lot of if statements, and probably you wouldn't be in the end a super 100% successful. On the other hand, if you show your machine learning algorithm a lot of pictures of dogs and cats, it somehow learns the generalized rules how to distinguish them and outputs a model that is able to achieve this task. So this is just like a philosophical difference. Either you go from input and program to result, or you go from input and desired result, your data, to a program that does very general things. A sort of prototypical machine learning model are neural networks. This is just one of the many, but it's sort of most standard way how to approach machine learning, and it's also a model we will use later in the lecture. How neural networks work, that really you have a layers of neurons that are connected by a weights. And really what you do during the training process is that you adjust the weights such that when you pass your input from the input layer to the output layer, you will get this desired result. Mathematically, what these layers do is very simple. They just do a linear transformation, and then that linear transformation is enhanced by some nonlinear function that we denote here by theta. And it's really just to add a little bit of nonlinearity, because not every problem can be approximated by a linear function. So you sort of do these transformations layer by layers. You have many weights for many neurons. And when you train the network, all these weights will be adjusted to perform your desired task. There was some math in it, but for purposes of this lecture, we can even zoom out a little bit. And really, what these neural networks do, that they take input and it's some abstract model that learns to approximate the mapping on the output that you want. Input could be a figure of a cat or the dog, and output could be a classification that tells you whether it's a cat or a dog. Now, in a quantum device, The input could be some measurement data, and the output could be the algorithm telling you, tune the voltage 3 down if you want to have a good operating regime. And this is exactly what we are going to learn in this course. Let me take a quick detour and mention why neural networks. So sometimes these sort of deterministic standard algorithms can work pretty well, especially on a smaller problems. Neural networks sort of generally has bunch of advantages that we can really take, that we can really use beneficially here in a context of tuning quantum devices. The first one is that they have ability to learn rules not just from any data, but from a really noisy data. And in measuring quantum devices, we have a lot of noise. And interestingly, a lot of that noise is really hard to characterize, characterize theoretically. So having a method that can learn directly on the noisy data is something that can be really beneficial. The next thing is a fast evaluation. Training these networks takes a while, but once it's trained, and the evaluation is really just some matrix multiplications. So it can be done very, very fast, especially if I'm comparing to rerunning an optimization program at the end of each data collection loop or something like that. And final thing are generalization properties. This is not even fully understood theoretically, but basically we learn that we train a neural network on some data and then on some other data that were not in the training set, that sometimes they are even a bit far from a training set, the neural networks can still perform reasonably well. Working with the devices that fluctuate in time, are noisy, having a good generalization properties for a robust tuning methods is again very desirable. Final slide of this section. Let us now collect all of this argument and just quickly explain how this works in an overall workflow. Basically, if I want to use a machine learning for experimental tuning, quantum dot or otherwise, the typical workflow will have basically 3 steps, so it's very simple. First, I will collect some data. Here is just a simulated data of a charge stability diagram. Then I feed it into the already trained machine learning model. The machine learning model is going to pop out, for example, a parameter value or some experimental decision. After this decision is made in terms of adjusting your tuning parameters, you go back, you collect more data, and you continue your loop until you achieved your desired